I'm David Onnen from the University of Oldenburg, together with some of my colleagues, some of them from DTU as well, some of them here in-house. I have looked at the topic of wake estimation. So we're constructing wake situations from inflow observations of a turbine. And we have taken this to the field. So I will report about some field experiments here. And I try to link it to some of the topics that we also discussed recently here in the context of the IEA Task 44. So looking a bit at instrumentation, at uncertainties, and some of the outlook, how we can proceed to use this. So that's our schedule for today. I briefly motivate. Then we look at some wake estimation methods, general overview, and then I explain the load-based extended Kalman filter, which I've employed here, more detail. Then there are details on the field experiments, results. Then we do a small excursion on analytical uncertainty propagation, continue the results, and then wrap it up. So why do we do that? We're talking of dynamic wake estimation. So we talk of the instantaneous wake position in relation to our rotor, relation to the wake exposed turbine. Potentially that can be used as a feedback signal for closed loop wind farm control, flow control, we could say. But also it can enhance the general observability or the situational awareness in our wind farm. We often see unreliable yaw encoders, so it's not even clear where the turbines are facing. And I will later show how we can also use the situational awareness generally. Now, this estimation task is not too easy because the wake position is changing. So we have a rotating turbine, and this wake is moving but leaving its footprint on the rotor. And this movement can be subject to wind direction changes, wake steering, dynamic wake meandering, generally many things that the atmospheric conditions can influence. The topic has been around for a while. So there are some concepts out there, some of the work we did, also some other groups. And there have been tests. Of course, there's simulation-based tests. That's very nice. You can test it in LES, or you can test it in aeroelastic codes with dynamic wake meandering models. There have been tests in the wind tunnel. And especially simulations and the wind tunnel, they offer something like a ground truth. So you can estimate your wake center, and you can compare it to a true wake center. That's not that easy in the field. There have been some experiments in the field which also looked at wake estimation, but it's always a difficulty in the field. What is your reference? What are you comparing to? So the goal here is to have a field experiment, but to have an independent reference to compare with. I'm not talking of a ground truth here, because in the field we have no ground truth, but that's why we will look at uncertainties and try to create a reasonable, certain reference signal to compare with. In that case, this is the lidar. So we will compare lidar-based estimation and load-based estimation. With overview of techniques, as I said, loads and lidar. For the loads, we usually look at blade loads, and then we have yaw and tilt moments, so the rotor imbalances, so to say. And it's often coupled with, for example, an extended Kalman filters or anything to give some robustness to the estimation and to formulate the workflow. We have reasonable time resolution, spatial resolution, observability. I'm just sketching it here. So we have a wake overlapping. We leave our footprint on the loads or on the load distribution along the blades. So we have some observability, not perfect, of course. No prediction horizon. Costs are usually low because we can assume, at least in modern turbines, that we have blade root bending moments probed. So from the turbine side, we have commercial readiness to employ. Here are some sources to check on some methods there. Then on the lidar side, we have to distinguish on the lidar type. So we can have staring lidar concepts. Here from Alan by Julio, for example, we see we have a few number of staring beams, and they probe at certain positions, and then we can couple that with an estimator to identify wake positions. The staring beams give you amazing time resolution, but usually not so much spatial resolution because we have just a few beams. Commercial readiness is, yeah, I would say between research and commercial. There are these staring beam lidars are definitely a thing already in the field, also in larger scale. Scanning lidar, since it's scanning, has low time resolution, but it has very good spatial resolution, good observability, good prediction horizon, but it's costly, and it will never be applicable for commercial applications. So what we're doing here is we employ the scanning lidar on research level to once validate our load-based approach, such that we don't have to leave it to the commercial applications to employ scanning lidars. Oh, should have showed you that plot. That's a kind of plot you'll see in the following a bit more. Now we dive into the load-based methodology. A bit of a block diagram. We have our wind turbine exposed to a wake, and we record flap loads, azimuth angle, rotor speed from that, and that enters our dynamic wake tracking algorithm then. It has some pre-processing before we enter the extended Kalman filter. In this pre-processing, we take the loads and we apply a Coleman-transformed or multiple blade coordinates. So we translate from the rotating to the non-rotating coordinate system. You see that here we have two different azimuth angles, and we always project the loads on the vertical and horizontal axis. That's quite handy because we have these signals in the yaw tilt and collective moment available at each moment in time. Next, we have a measurement model. Somehow we need to link these loads to the wake position. In this case, it's an analytical expression, which was derived here for the purpose. So an analytical model, you can see it here in the black dotted line, which is fitted to training data. In this case, the training data is generated in FastFarm. I've also worked with Hawk2 before, that works equally well. And what we see here in different colors is, yes, you see my hands, camera is on. We have a wake exposed turbine. We have a wake causing turbine in front. I do it this. And then we subsequently place the wake causing turbine at different lateral locations. Each of these lateral locations is represented by one color here. On top of that, the wake meandering model is on, so we get some variance in the wake position anyhow. And with very few simulations, we can accumulate very nice coverage of wake positions to populate our training data. One more thing, this model can be locally linearized, which is very handy then for the extended Kalman filter. Because extended Kalman filter means you have a normal Kalman filter, which usually handles linear operations, but you linearize at every operational point. Then the Kalman filter itself always compares what do I assume my state, how do I assume my state to change within one time step? How does it compare to the measurements? Here we see how the measurements are translated. The dynamic model, how does my state X change within one time step? For this purpose, we employ a stochastic process for the wake trajectory. So we model a random walk by manipulating the the noise that we feed to the Kalman filter. The conventional Kalman filter just handles white noise, but what we do some noise shaping by low-pass filtering it and integrating. And then we get a random walk which suppresses the high-frequency components, which means that if we have a high-frequency load event, which would suggest a very sudden change in wake position, that is rejected by this dynamic model of the extended Kalman filter. That's how these random walks look like. And this kind of stochastic modeling, that's I would say it's relevant at the higher end of our dynamic range. So at the spatial scales, which are really close to 2D, or the time scales of ambient wind speed over 2D. The slower changes of wake position, they are included anyhow by the slowly changing loads. So far for the methodology, the paper just got out, so you can read more on the details and the modeling in there. I think this is not the best environment to show all the equations here. Instead, we look at the field test now. The site and sensors. So it's in northern Germany. We have 2 wind turbines here, an upstream turbine, which is controlled, and a downstream turbine, which is mostly wake exposed. So you see that they are very closely aligned, 2.7D, super close spacing, along the main wind direction. We have southwesterly winds here in northern Germany. So it's a site really not made to profit financially, but made for research, you could say. And we have a nearby metmast as well. We have a nacelle lidar here on this turbine. We have yaw sensors on both turbines. And the campaign that I will talk about, or that I have in my data set here, it also contained a wake steering experiment. You will see here that within this yaw control sector, turbine 1 was toggling between wake steering and just conventional greedy control. There were 2 wake steering controllers active, one by University of Oldenburg, one by Technical University of Munich. It was a shared project there, and I'm not aiming at characterizing the wake steering itself here, but just as a disclaimer, we have some unintentional, but also some intentional yaw misalignment here in our data set. Yeah. The metmast itself, we have wind speeds, wind directions, also at different heights, so we can get shears. The scanning lidar here is a WindCube 200S, and we have 60 seconds per scan and an opening angle of 120 degrees to cover quite a wide range, facing downstream. And anything else to mention on the lidar? Not. And from the turbine, we have a handful of measurements. Maybe relevant here is we have power, blade root bending moments. The yaw is probed via GPS, which proved quite handy because on board yaw encoders are often faulty, and we have rotor angle. If we look at the lidar measurements now, you can see here the 2 turbines indicated, upstream turbine in black, wake exposed turbine in red. That's how the time series looks like. So, recording. That's the level of insight that we get. So you also saw some yawing in there, sometimes misalignments. We see how the wake propagates, how it overlaps. That's the kind of data we are dealing here with on the lidar side, and that we can use to reference our load-based. Starts again. Yeah, load-based control. The data set. It's not huge. It is a relevant data set. Here I show what kind of conditions we have. So we have wind speed, shear, turbulence intensity, wind direction, which is of course constrained just to the wake containing wind directions. We also are constrained in time. We exclude night times because there was this noise reduced mode in night times, so different turbine behavior, which we didn't want to have in the data set. We see in general the wind speed distribution resembles a viable distribution, but it's not fully converged. So we can say we have a useful data set here. It's not a fully converged data set. That's how I would describe it. We have a site with rather high shear. It's also maybe connected to the fact that we exclude night times here. So rather high shear, rather low turbulences, and as I said before, intentional and unintentional yaw misalignments. Now you see here the wake positions, which were extracted from the LiDAR data. So from our 1,800 samples, that's all the wake positions that were covered. In red, you see, I would say, the geometric view on it. So if you would assume the wake to just propagate in parallel to the wind speed, you would see this very idealized assumption of where the wake would be. But we see that when we probe it from the LiDAR, we get a lot more variance. So the wake is not, or the assumption of the wake just propagating downstream is not fulfilled. We see more variance around. Some of that could be explained by the yaw misalignment, because we know that yaw misalignment causes wake shifting. So I tested that here. I employed this Jimenez model based on the known yaw misalignment that we have. And we see that the order of magnitude of the spread approximately matches, but still it doesn't cover all the variance of the wake position. And on top of that, these are just scatters. They are not necessarily congruent in time. So takeaway from this plot is the LiDAR estimates help to give a reasonable assessment or reasonable reference for the fluctuant wake position. Now we need to know what kind of wakes we're even talking about. We're definitely in the near wake region here because we have such close downstream spacing. And here I have aligned all the wake deficits along their identified wake center. It's also a sanity check, so we can see that they are all correctly aligned to the center. It's a spaghetti plot, so wherever we have darker colors, we have more occurrences of similar wake deficits. What we see now is that we have quite some wake asymmetry. You see it especially as the ambient wind speed, and with that also rotational speed raises. Here from 7.5 meters per second on, it's more distinct. We have quite some wake asymmetry, one side being more pronounced than the other one. And we looked into that. One assumption is, of course, it's well known here in the context of wind farm control, curled wakes due to yaw misalignment. So here the data set was once filtered for yaw misalignment. So in black we see small yaw misalignments, and then in red and blue positive and negative ones. We see a small influence, but I would say the data set is too small to draw conclusions here. And this was also not the focus of the study. So there might be a small influence of curled wakes as we expect them here. There's a wind tunnel study of Jan Bartel, for example. That's how it could look like. But more relevant in this context, we found the impact of shear. So here the data set is, again, for just one wind speed bin, filtered for the shear coefficient. And we see that at very high shear coefficients, of which we have a lot in our data set actually, we see quite some wake asymmetry here. And the explanation which we assume to be the case, is we have wake rotation, and we have this shear. And the wake rotation basically causes an upwash of low wind speeds due to the shear on the one side, and downwash of high wind speeds on the other side, which then matches this asymmetry, which we see here, the deficit. This is, on the one hand, it's a finding here in our data set, which we found worth reporting, and we should have it in the back of our mind, because this asymmetry also touches the definition of the wake center. Of course, do we define the wake center as just the center of the momentum deficit, so the center of the total momentum deficit, or do we define the wake center in the sense of this middle point here between the two semi-peaks, or double Gaussian wake deficit? This cannot even be answered that clearly. I think it's just important in this context to report how the wake deficits that we're dealing with look like exactly. Now to the, say, most striking results, or most graspable results of this comparison. Here we have the wake position as estimated by the load-based Kalman filter and by the scanning lidar. So Kalman filter in black, lidar in dashed red color. And we have some instances marked here where we really see snapshots of what the lidar is showing at the very moment. Here at A, we have a partial wake one side of the turbine. Here at 0.5D approximately, which matches there. Here at B, we have a full wake situation, so close to zero. At C, we see a large ramp, and we also see some yaw misalignment here. Actually, you have two very different yaw angles of the two turbines, and we also see some expectable wake deflection due to the yaw misalignment. This overlaps with this very steep flank. So we had a yaw transient, and then we see this very steep flank, which was nice. Then at point D, we have a partial wake again. We also saw that there was quite some high dynamics happening here in between. So quite some forth and back, which was captured well by Kalman filter and lidar. So even at the higher dynamic ranges, we can follow these things. Then what we see here around E, we see that there's no more wake overlap anymore, which means this wake doesn't leave a footprint on the wake exposed turbine. And what we see is that the uncertainty bands rise then for the Kalman filter. The Kalman filter, here the uncertainty is quite straightforward because we have our state covariance. Kalman filter, each state is connected with a covariance, and that covariance is basically, square root of that is our uncertainty. It only works when the noise tuning is done correctly, but then we have a direct information on how certain we are. You can also see that here around B. That is a very, it's a full wake situation, I would say. And full wakes are a bit more difficult because there's no more yaw moment. So there's also slightly higher uncertainty, but here it really rises. But then again, for the lidar, what did we do here for the uncertainty? And here we have a little excursion. In the context of the IEA Task 44, we discussed a lot about uncertainties. What we saw going through existing papers, mainly type A uncertainties were used, so stochastic uncertainties. Not so much type B uncertainties, everything non-stochastic, device uncertainties, calibrations, and so on. Striking exception was this TNO report by Stoyan Kanev, which rigorously really looked at type E uncertainties and also handled analytical error propagation. And that's also what we want, or what we have applied here. Analytical error propagation of type B uncertainties, because that's what we need to handle all the uncertainties that come into the lidar processing. Just as an overview, the objective is to get the wake position uncertainty from the raw measurements of our lidar. So our lidar has elevation, azimuth angles, range gates, wind directions. Then we have the turbine orientations, because in the end, the wake position that we get is expressed in coordinates around the wake exposed turbine, turbine 2, this one. But what we have is some very different coordinate systems up front. I'm giving an overview here. So here's where the measurements take place, and then the uncertainties travel throughout all these coordinate transforms. You see it here on the left. I'm not showing this to replicate, but just to show how tedious it is, how all these uncertainties travel from here to there to finally get some proposition uncertainty. So in analytical error propagation, that's handled by these partial derivatives. So you differentiate with respect to certain uncertainty, and then you weave in your error. And at this point, it often becomes messy, because handling all these partial derivatives and the chain rules that come up when going through all these coordinate transforms, that's messy. Here I can give the recommendation, symbolic math toolboxes. I used MATLAB, for example. What you see here at the bottom, that's the very long output, which I would not have liked to calculate. It's just the output for the lateral wake position uncertainty. But what you can actually do is you define your symbols in the symbolic math toolbox, and then you differentiate with respect to these certain variables. So that was quite handy. It's something I can recommend. And then what do we get? These are the uncertainties of our coordinates first. So X, Y, and Z coordinates of where the lidar is probing. We're mostly interested in Y, so the lateral wake position. And we see this uncertainty, which we would have here, is actually quite small. So in our probing range up front of the second turbine, it would be around 4 to 5 meters. We also did the same error propagation for the projected wind speed, because the lidar always gives you the line of sight, but you have to project on the horizontal wind direction. So you can have some uncertainty on this one as well. And this one, we then plug into our wake center estimation method. So that comes next. What's the impact of the wind uncertainty on the wake center identification? Wake center itself is identified by a convolution. So we have such a wake deficit, and we convolute it with a square-shaped masking function of rotor diameter. It's shown here. That's the masking function. And it's a very robust way to identify the wake center here. And now we have manipulated the wake deficit by an order of magnitude, correlated bias actually, which was suggested by the previous result I showed you. And then we can see, if we zoom in a lot, the impact of this wind uncertainty on the wake position uncertainty. And we identified this to be rather small, but still we calculate this at every time step for all the wake deficits that we've seen before. It was calculated individually. So in the end, we have an uncertainty of the lidar wake position which varies. but it's usually at the order of 5% of the rotor diameter when you combine the pole position uncertainty and this identification uncertainty. How is that then used? I want to show some field results with performance metrics. One of the metrics is root mean square error. That's straightforward. That's average magnitude of the mismatch. And then we also use the uncertainty to say, okay, we have two uncertain things. We have uncertain lidar probes and uncertain Kalman filter results. And we have the so-called in-range metrics. So the share of samples for the mismatch is within the uncertainty range, which means we have two probability distributions, which represent an estimate and the uncertainty around it. And depending on how far away they are from each other and how big the uncertainty intervals are, we see, we make a case distinction, whether it is within this uncertainty range or not. And that is summed up then, and that's the other metric we see. Generally, we see that that this in-range metric is usually close to, I would say, between 90 and 100%. So it shows that within the limits of uncertainty, we get quite good estimates. Root mean square error shows some differences. The shear and the yaw misalignment, they have some influence, but it's at this point it's tough to really isolate, because we saw that the shear also touches the wake deficit itself earlier on. That's why it's hard to say whether the slight differences in root mean square error for the shear really originate from the shear itself or from the slightly different wake deficit here. What's quite expressive is that with turbulence intensity, also the root mean square error raises. That's expected. That's also what we see in literature. Coming to the conclusions. My time is nearly up here. Wake estimation. Here we see lidar and load-based wake position estimates agree rather well by approximately 0.2 d, root mean square error, and also what I just showed, around 90% within the uncertainty range. Atmospheric conditions influence, and generally we can capture wake constellations quite well. That's what we also saw in the time series there. In the context of wind farm flow control and IEA task, what we see here, this presentation, but also a bit more in the paper, we hope to show how you can assess performance in field experiments in absence of a ground truth, how scanning lidar can be helpful there. It's really in-depth characterization. So we're not talking so much about the about power ratios and these very global results, but really at wake shape level. Then general takeaway, GNSS probings for turbine yaw are definitely recommended, and type B uncertainties are relevant and not necessarily tedious. How to go on from here? In closed loop wind farm control, we could couple these wake estimation methods with wind farm models. There's some research, for example, by Markus Becker looking at Floridine, and coupling these models with the estimators could help, and then also weaving it in for model predictive control. But I think my point of view is that there are also limits here, because the wake position is changing at time scales at which you cannot control, or the meandering also is influencing so much that you cannot compensate that too much by control. So I think another field of application is also the more general look at situational awareness in the context of how you handle your farm. So inflow estimation here can be just one block, which needs to be assessed together with the grid and market situation, and to combine all these to an overall situational awareness, which can be used for decision making. AEP versus lifetime, do we meet grid requirements? Can we do something about load reduction? Which of the control modes that we have, both for our park, but also for the individual turbines, do we apply at any given point in time? That's it from me. Thanks a lot for your attention, and I'm happy for all the questions